way to figure out incomplete data is count stuff, right? Just count stuff, right? So if you're looking at a single column, a single field, you can count how many missing values with respect to the amount of data you have. So that's probably the easiest way to do it. Let's see if we have any. That's the easiest form of missing data check. So let's just look at missing data and completeness. Yes. Well, the first and easiest thing is to count things. Count things. Right? So one easy is count records missing values in a single column, right? So pick a column and count how many records have nulls there, right? Or, it could be something like, let's count records out of range, right? So maybe dates before 2000, right? Oh, these dates, or after today, right? So like dates out of range. Maybe you have some secondary data that tells you what the numerical values could be, right? So maybe the numerical values are out of range. Maybe you could do like an attempt at a conditional formatting, and if it doesn't format properly, then it's out. But typically, the easiest thing to do is count your nulls, and then if you have some range validity checks, just count for stuff that's out of range. Maybe you shouldn't have negative values, right? So you could count records with known defaults. Remember in the hurricane data set, there was a default, I think it was -999, right? So we go in and say count how many records have -990. So that's pretty straightforward. Now the harder thing is, how do we count records not there, right? How are we going to count records that aren't existing? If they're not in your data set, how do you count them? Well, you need an idea of what should be there. So let's see. I think I have an old Tableau from last year when I looked at the same data set. That's really annoying, you guys. I beat this data set just to smithereens last year. And where did I put it? No, that's the assignments from last year. It was under examples and solar power. Here we go. And let's just open up the workbook. All right. So first off, we can go in and we have our weather observations, and we have our weather observation time. So let's put a couple values on here just for the sake of it. And I take let's convert this to a continuous and an exact date. And I should be able to take the minute of it, I hope. Pause. Possibly not. Min, and, oh yeah, and I want to, let's see, I want to make this back discrete and, oh, there it goes. Okay, so that's the min, and let's put the same thing on here again. We'll make this an exact date. Now here in white. And I'm going to take the max of this. And make it discrete as well. So, so we have 617, we have 515 to 617. Oh, actually, the way to do this is we can actually use a Tableau quick calculation. So what I'm getting at is you need an idea of what should be there. So for that, right, you need an idea of the sampling process. Here we are, back to math again. Sampling process, right? But that's just a fancy way of saying what makes a unique observation. So for our weather data, a unique observation is one day. So for weather, it's one day and one station, right? I think. Was it one day? And no, it wasn't one day. It was 1 day times, times 24 times 4, right? There's 4 observations. But what you can do is you don't have to make your life hard and find, like, exactly how many records are missing. What you can do is you can just look for like entire days, or a day, like are there days where this is missing? So to answer that question, if you have 2 weather stations, what do you need to know about counting days in weather stations? Well, the number of days, right? And how many days were actually observed? Right, and I think it was like about 30, but what we can do is, I'm going to take this out. I'm just going to remove it. And we'll just use our I'm just going to use our date diff. Date part is, we'll count the number of days. And the start date will be the min of the weather observation time, and the end will be the max of the weather observation time. And just hit enter. Oh, and let's make this discrete. So 33, right? So we're partway there, right? We want 33 days of observation per station. So that's our goal. The question is, do we actually have 33 days of observation for each station? And what's the easiest way to do that? And this is like, I'm kind of giving away the assignment here. But the reason why I'm showing this is because I'm not expecting, like, I mean, you guys can go nuts formatting stuff and making it as pretty as possible, but the actual technique involved in assessing this by station is to put in the weather station identifier, for example. Do this. So we've got our 2. Oh, that's terrible. We'll put in the solar array instead. There we go. Got the 2 solar arrays in there, and let's just count the records. So just drop a count here. And come on. I want it to be we go. Weather station. Oh, right, because that's, I don't want to count. All right, so ideally, right, ideally we want 33 days from each weather station. The question is, how many days did we actually observe? Well, the next part is Tableau has count distinct. And we can do a count distinct on a time field. So if I just drag this over, I've got weather observation. I'm going to say count distinct. And that's going to give me a lot. But then what I can do is I can take count distinct and I can date truncate to the day. So I can say date truncate. Yep, that's okay. Date truncate, which part? Just the day, right? So it's going to truncate to midnight. And, oh, that's good. Interesting. Oh, the difference is one. I have to add 1 plus because it's not including the endpoint. It's not discrete. Okay, so our weather stations aren't missing any data, right? So they are. Well, they might be missing data. They might still be missing. They might still be missing. They might still be missing data. They might still be missing records. However, what we do know is that they've got every single day represented. Now, if we wanted to get into, if we wanted to count to see if they were actually missing records, well, how would we do this? What we would have to do is measure the difference in time. We could measure the difference in time in minutes and divide by 15. And that should be the difference. So this is difference by day. Let's change this to do difference by minute. By minute. And I think I should leave the 1 in. Do the day difference between the min and the max, and we're going to divide by 15. Because we're getting an observation every 15 minutes. So do this, and change it back to discrete again, just to display it. And then what I'm going to do is I'm going to replace this with the actual count of observations. And now we know for certain that there are, okay, good. Now we know that there are actually, somewhere in here, there are missing records. Because in between the start time and the end time, we have 3,263 15-minute increments. And I think I can take that +1 out. That looks like an error. That looks like a +1 error. So let's take the +1 out. Enter. And make this discrete. Yes, perfect. That was just a +1 error. Good. Okay, so how does this work? So again, we're getting back to the idea of what should there be. Well, the other way we can do it is we can say, if things, this is called our counterfactual, if things are collected, if observations are collected every 15 minutes, right? If observations collected every 15 minutes, then the minutes between first and last divided by 15 is the number of, and what's the special word here? Expected, right? It's what we expect. Expected records. So we expected for each weather station to get 3,263 15-minute observations every 15 minutes, because that's how many 15-minute chunks are in there, right? What we got was 3,182. Now that's, what you could do is name these nicely, turn it into a nice table with some illustration, and and maybe put a caption in there, and that would be enough. Full points.
What is the missing day, like, in which the editation doesn't happen?
Yeah, so that's the next question. Like, what more can we do? Now that we know that we've got some data missing, what do we need to do? We need to locate it. Where are we missing that data? So how would you go about trying to locate where that data is missing?
So are we counting like zero values, or are we counting no values? Because when I tried,
No,
there are some like zero, but they're
No,
not
we're not. So that's having records with missing values, right? That's not too bad to do because you've got the records there in person. What we're trying to do is we're trying to figure out when are there whole records missing from the database. That is, when was their data not being collected? And so that is the key question. When was data not collected? And the dead giveaway is the when, right? How are we going to figure out when data was not collected?
If the value is zero, do we call it missing value, or?
No, no, because, for example, with weather observations, your irradiance will go to zero at night. There's no sunlight. And if you get good cloud, if you have really strong cloud cover, your irradiance is going to get very, very low, right? The actual amount of sun, irradiance just measures how much sunlight is there, right? So zero is not a missing value.
It's when I check with the daytime, I see like there are some hours, the values are zero,
So,
but they're not known.
so what we're doing here is the first question another one here, and we've got our columns like this, and we might have some nulls, some empty strings, null, right? Or we might have another empty string here, right? So we can check for empty strings and nulls, for example. And so the first question goes up and down, right? It goes down through the records that you have, right? This first question only looks at what you have. Of the records, right, of the rows that you have, how many of them are, say, missing a date? How many of them are missing an explanation? How many of them are missing a type, right? You can check those. The second question is harder. The second question is about when should there be a record, but there is not. And again, the strong hint is every 15 minutes you're supposed to be getting a record. And so if we plot this on time and we count the number of records, we should always have two, right? One from each weather station. When it drops to zero, then we're missing something. So maybe we should just give that a try, right?
But that time can be a night, like.
No, but the weather should always be observed, right? We're always observing. The weather station's supposed to be on all the time. So let's just take our weather observation time as a column. Let's convert it into a continuous exact date. And let's just drop a count. Where is my count? Oh yeah, there is. That's my count. There we go. So again, you guys can take this and You can change the scale and the resolution, change it to like however you want to best illustrate it. This is, the scale of this is 1 record every 15 minutes. I know it says June 1st, but it's got one little dot here for every 15 minutes. And what you can see is that it goes along, and every so often we have a dropout, right? We've lost data every so often. Most of the time we're collecting data, and then every so often, boom, we're not. And it looks like we're losing data at the same time for both of them. We could color, for example, by, let's color. Why did that? Where did the zeros go? Oh, it drops down to 1 and 2. Oh, sometimes we're missing 1 record. So let's do detail. Why is that? That should be. There should be drops to 0, right? If I'm missing records. Let's change the marks to dots and make them very small. Oh. I know what it's doing. Here. So what it's doing is, we're counting the same problem exactly again, which is when there's no data, it's not plotting it. So each weather station is only producing 1 record, and it's not putting in the points when it's actually missing data. So what we can do is we can change the scale to the day, and we'll change this back to a line, and I'll change this to color as well. So we've got the 2 weather stations here, and now what we can see again. What we can see is that it's we do have variability in the data being collected. So what should we be collecting? Well, almost 100, right? We need 24 times 4, so that's going to be 96 is what we should be collecting. However, there are times when we've collected less than 96, and even more painful than that, using this method by itself, it still won't show days where if there's a time point where if there was a day where both of them were not collecting at all, it wouldn't show it. Now, fortunately, we already checked before, and we confirmed for ourselves that every day is represented at least once with both weather stations. So we're okay there. We're not going to be losing them. But what we are able to do is we can go in and say, hey, this is now a control board for our, we could turn this into this is the start of a control dashboard for our leadership team, for our to look at and say, oh, what happened on May 21st to this solar array? Why did we suddenly drop down to only having collected 68 observations when we should have collected 96? What was going on? Was it down for maintenance time? Was there connectivity issues? Why did that happen, right? If both stations were collecting weather perfectly the whole time, this line would stay constant at 96, right? You would collect 96 observations every day, because every quarter hour you collect an observation, and then another observation, another every quarter hour. What this tells you is that there are times when the weather stations are not operating up to snuff. They're not providing the data you're looking for. So basically, this is the heart of the more difficult question, right? The easier question is identifying when you're missing values in columns. That's not too bad, right? That's when are they null? When is it blank? When is it an empty string? When is it some negative number that's indicates a missing value. This is not for this data set. I don't think there is a missing value in this data set. The harder question is, how do you know when your system was not collecting data, right? How do you know when there's been gaps when the system was down and not getting data? And that's the tougher question that I was trying to get you guys to tackle with that first question, which is, yes, tackle this kind of as a warm-up, like as a dead giveaway, boom, go get those done. You could have done this with a measures value and measures table, right? Just done a bunch of measure values that just like aggregate over to say, count all the nulls and do one measure value for each column, for example. The tougher one that I was hoping you guys would sort of like figure out would be this bit of work, which is still just a counting problem, but you're having to count with respect to an expectation. You're setting up an expectation of, I want per weather station 96 observations per day. And then from here, you can get into doing things like putting in a control value, right? So I can add a reference line that is a constant, and I can set it to 96, and I can say custom value of ideal operation. Right. So, and then the sorry, the colors are terrible. Then basically this tells you that this gives like at leadership a quick way of saying, oh, here are the days when things were operating not as well as expected. And then you can do fancy stuff, like you can clean up the coloring here, and then maybe use conditional formatting to make these like points down here red, or stuff like that. But the important part is, we set up an expectation, 96 records per day. We measure what we actually got per day, and we illustrate it so that we can quickly see when things were not operating as expected. And I don't know if you've noticed, but there's things you can do with line, like you can change the path. I could make it square blocks like this. You can make it broken up steps. Let's see, I think I can make we can make the line thickness a little thicker to make it easier to see. Oh, there we go. That's a little bit easier to see, or even really thick like this. Right. So, there's all sorts of formatting tricks you can do. So does that help with that first question?
Yeah.
And again, this sort of data quality analysis, whether you're doing web traffic, you're looking at your call logs at a call center, your sales traffic. This is like pretty typical way. You'll have some criteria for how, particularly in a lot of the web logging systems. If you're like monitoring performance of a server, it's going to be like tracking something every 2 minutes, right? And so you can say, oh, well, if I'm tracking everything every 2 minutes, then 30 times 24, that's how many data points I should have in a day. And you can quickly do an illustration to show when your logging rate has dropped below what your threshold is. And you could set a threshold, like you can say there could be some intermittency, so we can capture. It's okay to capture up to 1 record per minute, and as slow as 1 record every 4 minutes. But then, like if you're doing a record every 5 minutes, then you want to, have some sort of warning band. But pretty much like illustrations like this, and this idea of setting up an expectation and then measuring against it is pretty standard for doing control work. All right, so can I move on to the second question now? All right. Operational significant differences. Looking for 2 standard deviations seems fairly open-ended. Yes, it does seem open-ended. It's kind of sounds terrible, and the only reason I put it in there is because I happen to know there's some bad data in there. I just happen to know that there are some inverters that just if you plot their daily performance, you can just see that they tanked compared to everything else. So, the question is two standard deviations enough? Yeah, you know, you can go for like 2 standard deviations off. Most of those inverters are within a couple standard deviations of each other. Again, like if we had more time and we could have developed the math and stats before taking the visualization course, I could have thrown at you a more detailed question saying, hey, figure out the confidence bands based, assuming inverter performance is supposed to be normally distributed, figure out the confidence bands based off of the normal distribution given the time of day. There is an Easter egg in there, in that, where's my time of day one? This is one, yeah. Yeah, this is a, let's see if I can find something that's not so, that's the irradiation, that's fine. This is one of the good ones that I did. So what I did is I aggregated all the inverters together, right? I aggregated all the power from the inverters just using a simple sum. Or no, I did an average there. What did I, and yeah, I averaged over the time of day. So what I did is I actually created a time of day calculation. Again, I'm not expecting you guys to come up with this. This is just to give you confidence that one station is working really well and one station is not, right? There is data in there. There is actual data in there where you can clearly see that one of the power stations and the whole power station as a whole is not operating up to snuff, and that is because there is a set of inverters in there that are actually underperforming, that are producing much less power than everyone else. So I did it by time of day because I like, it was kind of intuitively how my brain works. I wanted to see how things were working on average over the day. But you can do it by using histograms of power output and just showing that there are points that are way out. You know, there's a sort of a normal histogram, and then there's points that are lying very, very far out. 2 standard deviations, more than enough to catch this. And I believe I'm using my width here. What am I using for my width? I have a pre-calculated interval. That interval is probably, I think I'm using 2 standard deviations for that interval. Or it might be DC power interval. DC power interval width. Set it back and see what it did. Look at that. What a good guess by you guys. It's like you had actually taken the class last year. Look at this. 2 times the standard deviation of, I did 2 standard error multiples of the standard error. And what those multiples are, and the reason why I have 2 is because I have to go above and below the line. The line starts at the bottom here and moves upwards, or the band. Now, here's my standard error multiples. I'm using 6 right now. That's my highest one. 2, it gets really narrow. So this is another kind of like little hint that you can do, is if you don't know whether to go with 1 standard deviation or 2 or 3 or 4, put a parameter in that goes between like 1 and 6, right? And then you can adjust it to see how it displays. Right?
What is the standard error?
The standard error is the standard deviation divided by the number of observations. And again, it's kind of a shame that this isn't a 2-year program where the first year we can kind of get you through all the maths of data analysis and get you through the linear algebra, some calculus, probability and stats. Ideally, a probability and stats would be a 1-year program. It would be 2 semesters long. In an undergraduate setting, it is. this is highly compressed, so I don't get the opportunity to develop the stats before throwing the visualizations at you. But we have covered enough that if you take the standard deviation and you divide it by the number of observations, that's your standard error. And then if you're, anytime, what I've found in practice is anytime I hit a point of ambiguity where I'm like, do I want, do I want 1, 2, 3 standard error multiples? I'll just put a parameter in so that I can slide it back and forth, or so that the user can slide it back and forth and say, oh, let's take a look at 3. So, if we were going, so what this tells us is even at 6 standard errors of width, the two performances are very different, right? So that's like, you're statistically certain, right? This is like physics, this is like particle physics level certainty that you've got a problem with 4136001, right? And if there's anything that you guys, if there's any, like, I know you guys are worried about like getting something absolutely right or absolutely wrong. The only sort of like blanket yes, no question that you could totally bail and get wrong is not identifying that this station is out, right? Because if you actually genuinely play around with the data, you play around with it long enough and you will notice that this one station is out, that it is not producing the same amount of power as the other one. What it's doing is during the day, by about 9 o'clock, it hits a threshold and just can't produce any more power. And then once the sun goes down, it just stops producing power. So does that help with the second one? I think the biggest thing is if you're uncertain about how many standard errors to use, just put in a parameter and play with it, right? Because then that allows me to play with the parameter. I can go in. The challenge isn't picking the standard errors. The challenge is how are you going to illustrate it? Right? How are you going to show that one power station is not working as well as another? And then the even more difficult thing is how would you show that it's particular sets of inverters, right? It's not all the inverters in the power station, but it's a subset of them, right? And how would you figure that out so that you could display that pretty well? And here's the bad way. I don't recommend trying to do this. I think this is each and every single inverter in here. Is that what I did? Yeah, I think I overlaid every single inverter in here to see how they were performing. Maybe. Oh, that's efficiency. That's not. DC output power, DC power. So it's. Oh, that's what it was. I think. Is it DC power is. Yeah, so what's going on? Yeah, and I kind of gave away a little bit more of the assignment. That is, both DC power and AC power are limited, so it's actually not it's not individual inverters itself, it's the power supply going into the inverters. There's something wrong with the power supply that goes into the inverters, and some of the inverters are not getting as much power into them as other inverters. So it's on basically the conclusion is, to give away a good chunk of the assignment, the conclusion is it's on the input side. The actual things that turn DC to AC are working okay, but the amount of power flowing into some of the inverters is a lot less. And then the trick is to figure out which inverters are receiving. Is it all the inverters in this, or in 413601, or is it just some of them? And I wonder, I have this by all, I think, let's see. What happens if I do, I'm just gonna drop my inverter ID in here as well, into my detail. Yes, there we go. So, I just wanted to make sure that it wasn't a problem across all inverters. So, what this tells us is that there are some inverters in here that are receiving individual inverters that are receiving substantially less power than other ones, right? So there are a lot of inverters that are up here following along the upper axis, some that are getting kind of close, but then others are just completely falling behind. And let's just duplicate this. And I'm going to take this one, which one is AC, DC power. This is lower interval, I'm gonna take that away. And I'm gonna make the size really thin. And then I'm going to color by where did you go? Inverter, solar array, identifier color. There we go. Okay. So again, kind of giving away some of the assignment here. This is just one way to do it, but what you can see is the power going into the inverters for this solar station is very consistent, right? There's a few kind of dropouts that aren't performing as well, and you could highlight those, right, and say, hey, these particular inverters on the station 40 on the station 35 looks like they're starting to fail, or looks like their power supply is starting to fail. But then the main question is, why is there such a large amount of variation in the power going in? Basically what's happening is the solar panels themselves are not consistently providing power. The solar panels for 36 are not consistently supplying power. So what you would take back to executive in language that they would understand is, let me see if I can remember this right. It's, how do they put it? What is it, mean? Increase in the mean, decrease in the variance. Basically, you would go to them and say, there's wide variance, wide variability in the performance of the solar panel. It really needs investigating, right? So that the problem just isn't that it was low. The problem, being low is part of the problem. The other part of the problem is the huge variance, right? And in a lot of business functions, minimizing your variance, minimizing your month-to-month variability, creating consistent results is like core to efficiency, core to being able to produce predictable, industrial output so that you can make a profit. Variance is often the death of profit, right? If you have a large variability, your profit is going to tank, just because you're always dealing with changes. Whereas if you reduce your variance, your profitability goes up. And I can't remember, if I can remember what the term is, but there's a famous management term about like increase the mean, decrease the variance, and that's how you make money. All right, so does that help with question 2? I think I pretty much murdered that one. And our two separate items, the temperatures are two separate things and have two different calculations. Yes, there are two different temperatures in there, and they have different impacts, right? Let's go back to weather observations. And they actually occur, modulating operating temperature. So the ambient air temperature is exactly as it sounds like. It's the sun exposed temperature in the actual air around the system. Things should be relatively independent of that, but not completely, because it affects how quickly the station can cool itself. Modulating operating temperature is the big thing that impacts how well the system runs. And I think I actually, where did we do this? Inverter efficiency, maybe. Again, this was a thing I did. It's massive overkill. I'm not expecting anyone to produce anything with this much detail. Basically, I looked at the ratio of output to input, right? So the output will always be less, so that's AC power divided by DC power, right? So I look at that ratio, that's the efficiency of how well it's working. And then I plotted that efficiency for every single observation. So like the thousands of observations, I plotted that efficiency, which is a number between 0 and 1. And in this case, it's actually a number between 95% and 99%. I cheated a bit here, right? Because you notice I used the cheating technique of truncating your y-axis, which you're really never supposed to do. And I also truncated the x-axis here so that it starts at around 20 degrees Celsius. And then what I did is I just plotted 1 point for each observation, what the efficiency was versus what the module operating temperature was. And the efficiency is, I mean, it is straightforward. It's AC output power divided by DC input power. And this is per inverter. Overall, if you were going to do the, there we go. Get rid of this for now. So this is, so we'll do two efficiencies here. One is, this is per inverter, I'm gonna say individual efficiency is just the column AC power divided by DC power, which is the same as in divided by out divided by in. It's the loss in your pipe. Your pipe's a little leaky when you're changing your flow, and so it's your inverted out. Now, per grouping, so it could be by day or plant. Then a group efficiency is going to be a sum of AC power divided by a sum of DC power. And this is similarly, this is total out over total in. Right, that's all we're doing. We're just saying, instead of looking at the individual behavior, we look at the aggregate behavior. And the trick to looking at the aggregate behavior is to sum first and then divide. It's tempting to just sum over these efficiencies, but that's not the same, right? Because what that ends up being is a, if I were to sum over this, it would be some A over D plus another A1 plus another A2 over D2 plus so on and so on, right? It'd be things in ratio over it. Whereas this one is A1 plus A2 plus divided by D1 plus D2 plus dot dot dot. The critical thing is the critical thing is if you're doing any level of aggregate, you're going to need to do this calculation for efficiency. If you're using completely disaggregated, right, completely individual data, then you can use this. So, for example, what's an example of an aggregation I can do? Well, I could bin by degree Celsius, right? So I could create between, let's say, between like 15 and 70, I could create 1 degree Celsius bins, bin my records together, right? And then I would have to use this to create an average efficiency at that temperature, right? And from there, you could digest all of this into what would be just a single line over your 1 degree bins. I think these are measured to like 1/10 of a degree, or maybe they're measured to 1 degree. I can't remember. Let's see, what are they being measured to? Oh, 2/10 of a degree. So they're being measured. It's overkill, but sure, yeah. The important part is like what I'm looking for is some sort of graph. X and Y's can be reversed. You can play with color it however you want, of temperature versus either individual temperature versus efficiency. And you can either aggregate to some level and just make sure you use an aggregate measure of efficiency, or you can disaggregate and you can use this. And honestly, if you disaggregate completely on your display and you say my level of detail is going to be like every individual record, then this sum becomes this, because there's just a single value in the top and a single value in the bottom. It just becomes AC power over DC power. So there's almost no harm in just by default using the ratio of sums to get efficiencies. And what you can think of this is you're adding up all the different outputs, right? You're adding up every little output, right? And so you're taking all the little pipes and adding up to a big pipe. And then the bottom is all the inputs. So you're adding up all the little pipes that go into the input, and then you're taking the ratio of the two. And that's like how much out do you get for how much in? Does that help with question 3? Or does it just make it more confusing? I swear when I was thinking through those questions, I had actually done the work before. Like I knew the data's in there to actually be found. Like there were prompts. Really those were prompts to get you to kind of like explore and dig into the data, because I know it's actually hiding away. They're nice cookie crumbs and Easter eggs hiding away in that data set. And they're not as all as dumb as that stupid thing where you had to multiply one record by 10 and the others not. I mean, that drove me nuts. But yeah, there is some real stuff here where some of the data does not plot as well as other data. But the biggest thing that I was hoping you guys would kind of like catch on to, the absolute biggest thing that I was hoping you guys would catch on to, oh, where did it go? My duplicate, was this, right? Again, I've done it by time of day. You don't have to figure out how to do it by time of day, however you want to get at it. So I guess the fairest thing to do is I can set you on the path. I can say, look, I promise you the solar panels are behaving differently. Find the best way to tell me that story. This is my way of telling the story. Go nuts. Try to figure out the best way to tell that story. That story is in there to be found, and it's in there to be told. I just need you to exercise the visualization skills you've been practicing to tell that story.
So basically, with inverter 36, the plant 36.
Yeah.
Now, is it the solar panels or the inverters that actually?
So this is the DC power. So that's what's going into the inverter.
Okay.
So what's going into the inverter is failing.
Okay, so that was the solar panel.
Yeah. So it's something's wrong with the connection from the solar panel into the DC inverter. But really, what I knew ahead of time that there's discrepancy in the data, right? One set of data looks really good, and the other set of data looks terrible. And I was really hoping you guys could like sort of find that on your own. But what I'm happy doing is to just give you the hint that it is in there, right? And what I want you guys to really focus on is telling the story of the difference between the two solar panels.
What does the term solar array actually mean?
That's
it's just an solar area?
Array.
Array. Oh, yeah, an array.
Combination of.
Yeah, let's just show a pic. You know what? I should just Google a picture of a solar solar power installation. And let's just do some video. Let's just do an image and solar power installation. Farm. So yeah. Right, so an array can either refer to like all of these, like the whole thing, or just a single row, depending on how they've configured it. But basically it means,
Combination.
yeah, a combination of them. If you look carefully, these are kinds of gridded up, and each one of those grids constitutes a unique electrical connection, and then all those electrical connections get joined together into a big master electrical connection. And those electrical connections get joined together into bigger, and it's a process of aggregating.
So in our plan data, what actually are solar arrays?
Oh, you mean like in terms of the data?
In the actual data,
Yeah. So it's like in terms of the actual data relationship. Functionally, you have two weather stations, right? One weather station is associated with each solar array. And so functionally with the data, it's a way of linking the inverter, which each inverter, you have multiple inverters attached to an array. So we have, so for one array, right? So for one array, we have many inverters. This is a database diagram, by the way. It's not a physics diagram. And for one array, we have, and this is typically done like this. For one array, we have one weather station. And for each inverter, for one inverter, we have observations. We have one inverter has many observations. And likewise, one weather station has many observations. In terms of the data set, the solar array, or what we've called, the inverter solar array identifier. The identifier is a way of linking your inverter observations, right? You have an inverter observation. From the inverter observation, you know which array you're in. From your array, you can look at which weather station, and from the which weather station, you can link by time of day to the observation. So it's a way of creating, so day and solar array ID allow you to link your inverter observations to your weather observations. And you can see this in in the data source.
is the source code the solar array?
So, what's that? Is sorry, I'm just going into the data source here. Let's go back out. And last year examples. So we've created a relationship here, and the effect of the solar array identifier is simply to be able to connect the inverter records to the weather station records, and then we just make sure the exact time matches as well. So every 15-minute observation of the inverter output or inverter performance is linked to every 15-minute observation of the weather. And the way it does the linking is it says I have to match on the array identifier that's held by the station and held by the inverter, and then I match on the exact time of day. Does that help explain how functionally solar array impacts the data?
Yeah, I got how functionally it performs, and I was just wondering, how is, like, in the actual data,
Yeah.
which column reflects the inverter solar array? Is it
Oh, the
solar-
actual, you mean which column reflects the identifier?
Yeah.
Good question. So let's open up the CSV file, because I think, oh, actually, I can go back to data sources because it'll have the original name in there. It should. I want inverter observations. So remote field name. Plant ID is what I've called solar array identifier. That's just the plant ID. And likewise in weather observations, it's called plant ID as well. So the effect of this link is to link plant ID on plant ID and date time on date time. So the uppercase fields here are the ones that are in the original data source. So we have a date time field in the original data source, a plant ID, a source key, which is a lengthy, not helpful key, the DC power, the AC power, the daily yield, the total yield, and then the rest of those are internal calculations that I've done. Likewise, in the weather station data, we've got a date time, which is great, and a plant ID, so we can link the two together. The source key we could have used, but it's redundant. And then we've got the ambient temperature, module temperature, and irradiation, and everything else are just calculated fields. Does that help?
Are solar array and solar modules the same?
I think I probably do. Yes, the module operating temperature is the operating temperature of the entire array. So that's like what the temperature of the internal electronics are operating at.
So the largest unit is the solar plant, and then we have the solar arrays or solar
The same,
modules.
solar plant and solar array are the same idea, are the same
And
thing.
then on the solar modules or arrays, we have the inverters.
That's right. So an array is an array. So this is the same thing. This equals plant. The solar
I guess
plant.
plant is bigger.
No, it's the same thing. Just same thing. I just renamed it. Yeah.
So, in a practical context here, inverter temperature and module temperature, they are different. Because the module temperature is
Oh, I don't. No, they're the same thing, right? Because we're not. There is no inverter temperature in here, is there?
No.
no. But I was a question.
Yeah.
In one, it's specified.
Yeah,
inverter
okay,
temperature.
I-
So,
It's just that.
Okay. So yes, I was not. You guys are right. I have not been careful with my synonyms. So I did not edit that well enough. Interchangeable terms that I use. So plant and array I used interchangeably. Unfortunately, that makes the language really difficult to do. The other one that I used interchangeably is
Modules,
yeah, module temp and inverter temp. Inverter temp I used interchangeably because I made an implicit cognitive link that if the entire unit is operating at this temperature, then the inverters are operating at that temperature, and it was just like I apologize. I should have said plant all the way through, and I just should have said module all the way through.
Because practically, when the temperature of an inverter increases,
Yeah.
the efficiency reduces.
Yeah, practically.
Yes,
yeah.
and
Well, no,
module-
and actually, if you look at the curve, there's an ideal temperature that it works best at. If it's too cold, it doesn't work very
yeah,
well.
and module deals with like the array temperature, and when
Yeah.
it's high, then there is an increase in efficiency. So
Yeah.
when we saw the two terms,
Yeah.
because I like from someone with experience, when I saw the two terms, I just assumed they are different they are
Yeah.
different. But that was the way I calculated it. I tried calculating the inverter temperature using the
Yeah.
calculating field with the existing ambient temperature, and the values I got were similar to the module temperature. So I just assumed, yeah, he actually meant inverter temperature in this situation.
Yes,
Yeah.
module temperature, I should have just said module temperature, throughout the whole thing, as opposed to saying, I did not clean up the language in that nearly well enough. When I say solar array, I meant planet, and when I say planet, I mean solar array. I apologize. That was that was bad editing. And same thing, in the description, when I said module temperature, I also mean inverter temperature. When I say inverter temperature, I mean module temperature. And it's one of those things where I was just making cognitive leaps too quickly. Like I was just associating things too fast and not stepping back and thinking about the audience. Like, oh, does the audience know what I'm already thinking in my head? No. So I need to go back and re-edit to take out the stuff that I left ahead with. I think those are the two big ones where I kind of like made sort of automatic leaps. What the other one that I'm gonna let you guys go in a couple minutes, like right now, is I did preserve the word irradiation. Okay, I was worried that they called it something other than irradiation. And date time is what I've called observation. So let's just write that out. Date time, I've called it also observation. And sometimes observation time, right? So that's another set of terms that I used, unfortunately, interchangeably. I should have just stuck to these names, right? The names that's actually in the CSV file, instead of flipping over to synonyms for those. So does that help clarify like why the language is like how to map the language to the actual fields in the data set? Yeah?
Yeah, we have the total use and reuse.
Yeah.
But it seems that we don't use.
No, we didn't. This was more looking at the individual time units. It's a bit of a make work thing, but one of the things I could have done is you can actually the daily yield you can actually calculate by summing the AC power per day. So what you can do is for each day you can compare the sum of AC power on that day versus the daily yield on that day, and they are for the most they're within like milliwatts of each other. They're very close to each other. Like they're different by rounding errors mostly. That's that's the big reason I didn't use those, is because daily yield is no different than simply saying sum AC power over the day. Total yield is a cumulative sum taken every. The total yield is the cumulative sum of AC power reported at midnight of every day. So if you did a running total and reported the value of that running total at midnight every day of AC power, that would be the total yield. With the exception that on the very, very first day, there's already a non-zero total yield, which is the total yield over the whole prior lifetime. I didn't want to get into that because that is actually another confounder in there. The longer these systems get used, they wear down and they don't work as well. So there is a hidden confounder in there with total yield. I didn't put that in the assignment on purpose because it complicates the analysis some more. And I wanted you guys to work on a lot of different stuff, but I didn't want to throw even just one more thing to confuse things. And what you would have to do to use total yield is you would want the total yield on the very first day, basically, to know where your offset is. So That's why they're in there, but we didn't use them, is because they're for the most part kind of redundant, right? One's a cumulative sum and one's a sum over the day. But they came in the data set already there. All right. Okay, so I'm gonna let you guys go. It's 10 to 5. It is now like almost completely dark out. So, does that, like, do you guys feel more confident with the
Sorry,
assignment?
can we go back to the mail? Let's see if we,
Which one?
the mail Ryan sent. If, so we can just,
This guy?
no, the mail.
So
So,
the-
yeah, the email is sent.
Oh, the email,
So,
yeah. Is
yes.
there one more question? Yeah. Oh, a review of the first assignment.
I think
Okay.
you kind of covered that though, I think,
Yeah.
with some of the things that, like,
Yeah, I mean, like, I can't emphasize enough that overall, like, asking these questions is the right direction to go. Like, this is the biggest thing, that was the most impressive thing about this. As soon as I read this, I'm like, oh, you guys are getting what it means to be a data analyst. So,
Thank you, sir.
all right, thank you very much.